Hi everyone. So in this video we are going to start a new series of reactions that belongs to the phenols, and these reactions are known as electrophilic aromatic substitution reactions. Okay, these reactions are actually the characteristic or reactions of the aromatic compounds such as benzene and the related compounds, and phenol also being a aromatic compound. These phenols also show the aromatic these electrophilic aromatic substitution reactions. And in this video we are going to discuss the nitration, which is one of the types of electrophilic aromatic substitution reactions. Okay, so this reaction will be discussed in detail, and in the subsequent lectures we'll also discuss the other reactions, other electrophilic aromatic substitutions such as halogenation, sulfonation, Friedel-Crafts reaction, Kolb's reaction, and many other reactions. Okay, we'll discuss the first of all we'll look at what actually the electrophilic aromatic substitution reactions are. Okay, so these are the characteristic reactions of the aromatic compounds. Okay, so that's why we call them as the electrophilic aromatic substitutions. In this reaction the electrophile is on work. Okay, so electrophile is an electron deficient species, which is positively charged and needs electrons. It's in dire need of the electrons. It is deficient by the electrons. It is electro-loving. It's electron loving, means it is positively charged and loves the negative charge. Okay, it's electron loving. So in these reactions, these electron deficient reactions are substituted. The reactions are actually substitutions in which once one of the species is replaced by this electrophile. So the reactions are the electrophilic substitution reactions, and the substitution reaction take place on the aromatic compound. Okay, the aromatic ring of an aromatic compound. Okay, so this is what actually it involves electrophilic aromatic substitution reactions. Okay, these are electrophilic substitutions where an electrophile is substituted to an aromatic system. So these reactions, in these reactions there is a breakage of a CH bond, a carbon hydrogen bond is broken, and in place of that a new carbon electrophile, a bond between the carbon and the joining electrophile, substituting electrophile is formed. Okay, here as we have taken the example, E is generally we represent E here is represents the electrophile. Okay, so these reactions are the characteristic reactions of benzene. Benzene is a very well-known aromatic compound, and we have other we have other aromatic compounds which are electrophilic aromatic in nature. For example, we have phenols, we have many other compounds as well. Okay, so these reactions, unlike alkene aromatic compounds, they do not undergo the addition reactions. There is no addition reaction, because if we look the reactions of the alkenes which contain the pi system. For example, if we take this example, this is a pi system of an alkene. We can have more than one double bond. So these alkenes, the characteristic reaction of the alkenes is addition. There is addition across this double bond. But the benzenes, which also have the aromatic compounds which also have the double bonds, these do not undergo addition reaction. So addition reaction is not a characteristic reaction of the aromatic compounds. Rather, there is substitution takes place. Why? Because the aromatic system is sufficiently stable. It is sufficiently stable as compared to the alkene. So there is no need, it is not in need of new species. It is not in need of the electrons. The ring has a good electron cloud. It has a good electron density. It is sufficiently stable, so it doesn't need to undergo the addition reactions. Rather, it can undergo substitution reaction. That is, one of the carbon hydrogen bond is broken. Okay, and in place of this a new species in the form of the electrophile is added to this place. Okay, so these are the electrophilic substitution reactions, and generally we need the Lewis acid as a catalyst in these reactions. We will look at these reactions in detail. Here we have an example. This is a benzene, and benzene, we have this carbon hydrogen bond, this is broken in this case, and this is the electrophile with a positive charge. So this is electron deficient species, that's electrophile. So the carbon and electrophile bond, this bond is formed, this Ce bond is formed in the reaction. Okay, so this is the general representation of electrophilic aromatic substitutions, but here we are concerned with the electrophilic substitution reactions of phenols. Okay, because phenols also phenols have a hydroxyl group. This hydroxyl group is the activating group. It activates the ring towards the electrophilic substitution reactions. The electron density of this ring is increased by the presence of this hydroxyl group. We have a lone pair of electrons which is in conjugation with this ring, as we have already discussed. This increases the electron density of this ring. As a result, it makes it a good substrate for the reaction towards the electrophilic substitutions. Okay, so that's why phenols are also, they undergo the what you call as the electrophilic aromatic substitution reaction, and they usually undergo the poly substitutions, means there is a substitution at more than one place on this phenol ring. Okay, further, what else we have to remember, that the hydroxyl group activates this phenol ring, the ring of the phenol, this benzene ring, this aromatic ring, more at ortho positions and the para positions as compared to the meta positions. Means these ortho positions and the para positions, they are more likely to undergo this to this substitution rather than these meta positions. Why? The reason can be found in the what you call as the resonance structures of the phenol. If we look at the resonance structures of the phenol, then what we can look at, for example, if we try to draw the resonance structures, this is phenol. So for phenol, we have the hydroxyl group. We have already drawn these structures in the previous lecture, so we'll try to again draw. So these electron pairs they move towards the ring. As a result, this will be broken. This electron pair will move towards this carbon. As a result, this resonance structure is obtained. So we have a negative charge on this carbon, and we have these double bonds are intact, and there is double bond between the carbon and oxygen. So we have positive charge on this oxygen. So next resonance structure we can draw. These electron pairs are capable to move. They will move towards this carbon bond. As a result, these electron pairs will move towards the para position, to this para carbon. As a result, will be getting, we have negative charge on this carbon, and there is a double bond between this carbon and this, and rest molecule is intact. So next structure can be drawn. These pair of electrons will move towards this carbon, and this pi bond will be broken, and the pair will move on this ortho carbon. As a result, we'll be getting a resonance structure or double bond between this and this carbon, and there is negative charge on this carbon, and rest molecule is same. And in next structure, the fifth structure which we can draw, these pair of electrons will move, and these will move towards the oxygen. As a result, we'll be getting a double bond, and we have the phenol. Okay, so we can look at these resonance structures. The electron density, the negative charge is more on this ortho position than on this para position, than on this ortho position. Okay, at meta position we don't have that much of, there is electron density, but the negative charge, the more electron density is on the ortho and para positions. That's why we say that the phenol ring is more reactive at these positions. Means this hydroxyl group activates the phenol, the hydroxyl group activates the phenols, activates activates the phenols at ortho and para positions. Ortho and para positions. What happens due to this effect? The substitution, the electrophilic substitution that we are doing, the electrophilic substitution that we are doing will be at the substitution will be at ortho and para positions instead of the meta position. Okay, so this we have to understand. Now let's look at the first reaction that we are going to discuss here is the nitration of the phenols. And nitration is actually the addition of nitro group, that is NO2 group. This nitro group is added to the aromatic part of the phenol, that is this ring. Okay, so this is called as a nitration. If we treat the phenol with dilute nitric acid, okay, this is dilute nitric acid, and obviously it is in presence of an acid. We can write H2SO4 sulfuric acid. In the presence of the dilute sulfuric acid, we treat this phenol with dilute nitric acid. Okay, this is nitric acid. We get two type of substitutions. One substitution is at para position and one substitution is at ortho position. So this is para nitrophenol and this is ortho nitrophenol, or we can also call this as 4 nitrophenol and this is 2 nitrophenol. Okay, we get these two types of two different isomers of the same compound. Okay, so this can be obtained when we treat this phenol with the dilute nitric acid. When we treat it with dilute nitric acid in presence of acid, we get para product and the ortho product. We get these two types of products in this reaction. Again, we have to remember that if we look at the para compound, this para compound is less volatile. Okay, this is less volatile in nature. This is capable of forming the intermolecular hydrogen bonding. Means this phenol, the 4 nitrophenol or para nitrophenol is capable of forming the intermolecular hydrogen bonding with other nitrophenol molecules. As a result, this becomes less volatile. The ortho compound is going to form the intramolecular. There is the hydrogen bonding within the molecule. Okay, with the nitro compound. As a result, this becomes more volatile, and rather we can say it is steam volatile. It can be separated from this mixture by just the steam distillation. That's why what we have written here, due to the intramolecular hydrogen bonding, the ortho nitrophenol is steam volatile. Why? Because there is intramolecular hydrogen bonding, while the para nitrophenol is less volatile due to the intermolecular hydrogen bonding, and this causes the association of the para product of these molecules. So we can separate these two by the steam distillation. We may be asked sometimes this question, which of the two is more volatile and how we can separate. So we have the steam distillation is a separation technique that can be used to separate these two isomers of the nitrophenols. Okay, now if we react the phenol with concentrated nitric acid. In the previous reaction, we reacted it with the nitric acid, means dilute nitric acid. And if we react it with the concentrated nitric acid, obviously in presence of an acid, then what we are going to obtain? We will be obtaining 2,4. This is position 1, 2, 3, 4, 5, 6. So this is 2, 4, 6. Okay, 2, 4, 6 trinitrophenol. This is the polysubstituted phenol. Now, okay, we have obtained the polysubstituted phenol. So this can be obtained when we treat it the nitric with the concentrated nitric acid. Okay, so we have to remember, if we treat it with the dilute nitric acid, then we are going to obtain the ortho and para product. And if we treat it with the concentrated nitric acid, then we are going to obtain this polysubstituted. This is polysubstituted phenol. Okay, and this is commonly known as the picric acid. Okay, as we have shown, this is picric acid, the common name, and we have the IUPAC name is 2,4,6 trinitrophenol. And in this reaction, this compound is obtained in less yield, less quantity we obtain of this picric acid in this reaction. We have one more method to obtain this picric acid. How we can obtain a good yield of this picric acid by treating it with concentrated sulfuric acid first. Then in this case we'll be obtaining the disulfonic acid. We'll be obtaining the sulfonic acid. This is not actually di, this is we'll be obtaining sulfonic acid. One is this is called as the 4-pheno sulfonic acid, and this is 2-pheno sulfonic acid. Okay, so then we have to treat it with the concentrated nitric acid in presence of very very low heat, very low temperature. We can obtain this picric acid. This is picric acid. We can obtain this in good yield. Okay, we'll obtain this in good yield by following this path of the reaction. Okay, so these are the simple concepts that we have to remember. And if we look at the mechanism, then the mechanism is very simple. In this first step of the reaction, there is the generation of the electrophile. Okay, and the electrophile in this case is this is nitronium ion. Okay, this is called as a nitronium ion. This nitronium ion is the electrophile in this case. This is nitronium ion. Okay, so the nitronium ion is the electrophile that we were representing with E positive. So the E positive, E plus in this, that is electrophile in this case, is the nitronium ion. How this is obtained? First we have the reaction between the nitric acid. We have the reaction between the nitric acid and the what you call as the sulfuric acid. So since the sulfuric acid is a very strong acid, so the proton of the sulfuric acid will be easily obtained in a solution. So it will give the proton easily, which will subsequently be captured by the oxygen of the nitric acid, because oxygen has a lone pair of electrons and it is less acidic as in comparison to the sulfuric acid. So there is the formation of this hydronium ion. Okay, so as a result, there will be this portion will leave as water. This will leave as water in the reaction. Okay, this will leave as the water, and the remaining part we are getting is the nitronium ion. Okay, and there will be the HSO4 negative ion will also remain in the what you call as a reaction system. So in the first step we are getting the nitronium ion, and we can also represent the nitronium ion by this. We have a positive charge on the nitrogen in this nitronium ion, which is doubly bonded to two oxygens. So in the second step of the reaction, since this is the double bond of the phenol ring will attack on the nitronium ion, because we have more electron density on this ring, and this is electrophilic in nature, that is, it is deficient of the electrons, so it will attack on the nitronium ion. Okay, and we'll be getting this intermediate. Now we have a positive charge on this carbon here. So this positive charge will be balanced by this electron pair. So the hydrogen will leave its electron, and this electron pair will form a double bond between this carbon and this carbon, and in the reaction, the nitro group will be the nitronium ion, the nitro group will be substituted at the ortho position of the phenol. Okay, and in the reaction we'll be getting the H positive. In this step we'll be getting the H positive, the proton, which will react with the HSO4 negative, and will obtain H2SO4. So this H2SO4 acted as the catalyst in the reaction, and it was obtained back. So here the substitution took place at the ortho position. Similar mechanism we can show for the para position also. For this pi bond will attack on the nitro group, and will the substitution of nitro will be at the para position, and the same reaction mechanism can be shown. Okay. So this was a nitration of phenols, one of the electrophilic aromatic substitution reactions. In the subsequent upcoming videos, we'll be discussing other reactions, other electrophilic aromatic substitution reactions of